So welcome back, and in this little video we're just going to be looking at the enthalpy of hydration. That's what happens when our ions become completely surrounded by water so that we get that infinitely dilute solution. And we're also going to look at putting those two things together to calculate the enthalpy of solution, and we're going to look at lots of examples of those. And then very briefly at the end we're just going to talk about why that might not necessarily tell us if the salt is soluble or not. Okay, but you're going to need your solubility notes, and we're starting on page 5. Okay, so we're on the top of page 5 of your notes, and we're just looking at that hydration enthalpy. Now to start this off, I'm just going to draw the polar water molecule. So we have our oxygen, it's a bent shape, and we've got the lone pairs on the oxygen, very delta negative, and we've got two very delta positive hydrogens, making this a very polar molecule capable of doing hydrogen bonding. Okay, so when we actually get hydration enthalpies, we start here with our lattice. So this is our ionic lattice, and we have our polar water molecules. And we now have our hydrated ions. Notice that this negative ion here, it's these hydrogens, this delta positive end, which is orientated towards it. And here with the positive ion, it's the delta negative end that is orientated towards it. Okay? So this, as we've said, is an exothermic reaction, because if you actually look back at the definition, the enthalpies of hydration start with the ions in their gaseous state. So we're not breaking any bonds, we're only ever making bonds, so it's always exothermic. And as you would expect by now, the sizes or the strengths of these hydration enthalpies depend upon two things. And it's our old favourite, size and charge. So it's the size of the ions, and it's the charge of the ions. And we can see that down the bottom. So here we have the magnesium ion. It's small, it's quite highly charged. It's attracting a lot of water molecules very strongly. So it has a relatively exothermic enthalpy of hydration, okay, over nearly 2000 kilojoules per mole. Whereas sodium, on the other hand, it's a much larger ion, it's less highly charged, it's less able to pull in those water molecules to form these hydration shells, and it's got a much lower. Okay, if you do biology, you come across primary and secondary hydration shells in biochemistry. Okay, so thinking about the magnitude of the hydration enthalpy and how it's going to change on progressing. So we're looking here, as we go down the group, and as we go down the group, it's going to become less exothermic. Remember, it's better to talk about something becoming less or more exothermic rather than larger or smaller, because we're not 100% sure what that actually means. As you go down the group, they become a smaller negative value. The easiest way to say it is they become less exothermic. The reason for that is the charge stays the same, but the ionic radii increases down the group. So you've got less electrostatic attraction between the water molecule and the ion. As we go across, as we go from sodium to calcium to aluminium, they become more exothermic. The reason for that is the ionic radii decreases, in other words, become smaller, and the charge increases. Now that works for positive ions, but it also works for negative ions. So negative ions as well become less exothermic. So they become less exothermic as you go down the group. So it's the same pattern as it is for positive ions. Notice it has nothing to do with the sign of the charge, simply the size of the charge. Because in this case, it's going to be the delta positive hydrogens which are attracted to the ions. In the positive cases, it's going to be the delta negative oxygens. So it doesn't matter whether you're going down group 7 or group 1, they will become less exothermic. And for the same reason, the ionic radii increases. So the last question here, how do you account for the fact that hydration enthalpy of H positive is exceptionally large? Well, let's have a think a bit about what a hydrogen ion is. So a hydrogen ion, hydrogen positive ion, is a proton. And if we think about what the water molecule looks like, it looks like this, where we have that lone pair on there. Okay, so when we put those two together, instead of getting a hydration between the two of them, we actually get a full-blown covalent bond. The lone pair on the oxygen, or one of the lone pairs, is able to form a delta positive ion. Okay, because one of the lone pairs of electrons gets donated to that hydrogen ion, which forms a dative covalent bond. And this is actually what happens with an acid. Okay, hydrogen ions, we say the presence of hydrogen ions indicates that we have an acid. Actually, we don't have any hydrogen ions because having protons floating around in solution is highly unlikely. What we have instead is the hydrogen ions have reacted with the water to make this H3O positive ion. And that's why it's exceptionally large, because you're not doing a hydration enthalpy, you're doing a full-blown covalent bond here. Okay, so now we're going to put those two ideas together to calculate the enthalpy of solution. Okay, so to remember, to get something to be dissolved, we've got two processes going on. We're going to break up this lattice, which is why we've got this negative sign here, and then we're going to hydrate the ions. So we can calculate that looking at a Hess cycle. So if we look here at the Hess cycle, you've got your ionic lattice here, plus your solvent, this is water. Enthalpy of solution to turn it into aqueous ions. If we start from the gaseous ions, we can turn these gaseous ions either into the solution, aqueous, that would be enthalpy of hydration, or we can react the same gaseous ions to form the ionic lattice, that is lattice enthalpy. So again, if I want to work out this, I'm going to go against this arrow with this arrow, so it's going to be minus the lattice plus the hydration. Okay, so we can rearrange that at the bottom of the page to give us the other two. So if I want to work out, for example, hydration, that is simply going to be delta H solution plus the delta H lattice. And if I want to work out the lattice, that's going to be delta H hydration minus delta H solution, because I'm going to bring this over to this side to become positive, and then I'm going to take that over there. So delta H hydration, take away delta H solution. You can also look at that on the on the diagram here. If I want to work out hydration, this one is going to be plus the lattice plus solution. If I want to work out lattice, it's going to be this one. It's going to be plus the hydration minus the solution. So you can work out all of them. Okay, so we have a couple of these to try on the next few pages. So I'm just going to go through the first example with you, and then I'm going to let you have a go at the others. Okay, so we're looking to calculate the enthalpy change of solution of lithium fluoride, and we're given some data to do that. So I'm going to write down my equation first of all. Delta H solution is equal to delta H hydration minus delta H lattice. Now I can break that down into different bits, or I can do it all in one line. It really doesn't matter. So I've got my hydration, and I'm going to hydrate one lithium ion and one fluoride ion, and I've given the numbers for those there. So that's minus 519, one lot of that, and one lot of minus 506. So those are my two ions, which I'm going to hydrate, and I'm minusing the lattice. and minusing the lattice will always give me a positive number because the lattice is always exothermic. So I have this number, which will come out as negative, take away this number here. Now if I put that into my calculators correctly, I should get minus 3.0 kilojoules per mole. In other words, the enthalpy of solution is a small exothermic value. Okay, so moving on to the next examples on this page. Next one, we're asked to calculate the enthalpy of hydration of the bromide ions given the other data. You just need to be a little bit careful on this one because obviously there are 2 bromide ions. So we're going to divide our final answer by 2 here, and you should get this answer here, minus 307.5. One thing to remember with hydration and with lattice is they are always exothermic. So if you work this number out and it comes out as positive, you're wrong. You need to go back and check again. You've possibly got a sign in the wrong place. So just go back and check that. What this also allows us to do is to show the trend in solubilities, because we can now work out the enthalpy of solution for different sulfates, for example, going down group 2. So you should remember your trend in solubilities is the sulfates become less soluble going down the group. We can now see why that is from a physical chemistry point of view. If we work out the enthalpy of solution of magnesium sulfate, it comes out as a reasonably good exothermic reaction, so that's likely to occur. However, when we work down to barium sulfate, it now has an endothermic enthalpy of solution and is much less likely to occur. Okay, so what I'd like you to have a go at doing now is pausing the video and having a go at the calculations on page 10. So have a go at those ones. Okay, so hopefully you've had a go at these, and I'm just going to run through the answers, just check that you've got the right ones. So sodium chloride comes out as plus 3.9, then we've got minus 12, plus 17, plus 21, and the last one, last two, minus 156 and minus 138. Okay, now I would draw your attention to one of them, and it's one we're going to come back to again in the next video, and it is this. The enthalpy of solution of sodium chloride comes out as plus 3.9 kilojoules per mole. Now we've said that if the enthalpy of solution is positive, in other words, if it's an endothermic reaction, it's less likely to be soluble. But we all know, or we should all know, that sodium chloride, table salt, is very soluble in water. So this is a salt which is soluble in water despite having a positive enthalpy of solution, an endothermic value here. And that's something to think about. Okay, so that just finishes this little video where we've been looking at the enthalpy of hydration and putting them together to make the enthalpy of solution. And we left you with sodium chloride, which has a positive enthalpy of solution, and yet we know it is soluble. The other one we'd like you to think about is magnesium carbonate, which has an exothermic enthalpy of solution and is yet insoluble in water. So why is this the case? It's something we're going to be looking at in the next video, and as you might expect, it has something to do with entropy. But until then, take care, stay safe, speak to you soon. Bye bye.